So we're going to start right where we left off last time. And where we left off last time is during the last 5 minutes of class, I put a quadratic up on the board, and very, very quickly, and I know it was quickly, we started writing down a bunch of information about it. Does that sound familiar from last class? We wrote down the domain was negative infinity to infinity. We knew that because that's the domain of every single quadratic. We wrote down that it opens up. We know that because the number in front of the x squared is a positive 1. We found the y-intercept. Y-intercept is found just by plugging a 0 into the function and crunching out a y value. We found the vertex using our brand new formula, negative b over 2a. And we remember that that doesn't give you the entire vertex. That just gives you the x value of the vertex. To find the whole vertex, the ordered pair of the vertex, you then have to take this number, run it through the function, and that will give you the entire vertex as an ordered pair, an x value and a y value together. Once we have the vertex, we can also jot down the axis of symmetry, that dashed vertical line that goes right through the vertex. We can write down the range based on the fact that we know that our particular parabola opens up and the vertex is here at 2, -9. That's enough to give the range of the parabola. And then we have several different techniques of finding the x-intercepts. What we want is we want to find the zeros, and if the zeros are real, then the zeros are also x-intercepts. In this case, the easiest way to do it is to factor. But if you needed to, you could use the quadratic formula, or you could complete the square. And once we have all this information, we can actually draw a pretty accurate parabola. For instance, I can plot the vertex at 2, -9. I can plot my two x-intercepts at 5, 0 and -1, 0. I can sketch in the axis of symmetry. A good test you can do with your axis of symmetry and your x-intercepts is the x-intercepts should be equal distance from axis of symmetry. Because these things are all symmetric over the axis of symmetry, the distance from your axis of symmetry to each x-intercept should be identical. If it's not, then your parabola is not symmetric and something went wrong. What else do we have? We have a y-intercept. We have a y-intercept of 0, -5. And this is really slick, everyone. This is really slick. Every parabola is perfectly symmetric over its axis of symmetry. That works with the x-intercepts, and it works with every single ordered pair on the graph. So does everyone see how the y-intercept is exactly 2 units here from the axis of symmetry? That means there's another point 2 units away on the other side. So you actually get this point right here for free because of the axis of symmetry and your y-intercept. Everyone see how I get a free point there? That's pretty cool. This is probably enough to draw a graph, but if I ever want more ordered pairs, the way you find an ordered pair doesn't change. You plug a number into the function and you get a y value out. Now with this particular function, I can plug any number I want into it because its domain is negative infinity to infinity. But do I want to find an ordered pair by plugging in 100? No, because it's going to be way off my graph. It's not going to help me draw my graph at all. So while this isn't illegal, it's not helpful either. No. Pick x values close to the vertex if you need more ordered pairs. So the vertex is down here at 2, -9. So what would be a good value to plug into the function to get an extra ordered pair? What's a value that's close to 2? 1 or 3, yeah. And if you plug 1 or 3 into the function, you'll get -8. They both give you the same thing, and that's no big surprise to me because these things are always symmetric. Once you have your vertex and a couple other ordered pairs, you can draw a pretty slick graph. And remember, these graphs are not sharp and pointy. They're not like the absolute value function. They're smooth and curvy. Just like that. Smooth and curvy, not sharp. So we can jot down a whole bunch of information about any quadratic, the equation we're given. And from that information, we can usually draw a pretty a pretty good looking parabola. I just said they weren't sharp. What do you think about that, class? Is that okay? We're going to do another couple today, but is that all right for so far? Okay. Now, the next thing I want to say is this. In mathematics, we have multiple ways of writing the same thing. Here's an example. Do 1/2 and 0.5, or 5/10, as we should say, mean the exact same thing? Yeah, there's absolutely no difference between those two things. Now, some homework assignments are going to say we really want a decimal or we really want a fraction, but mathematically there's no difference between these two things. Here's something else. Check this out. Those are both equations for lines, but it actually turns out that they're the exact same line. There's no difference between the two. This one happens to be written in what we call slope-intercept form. Does anyone remember what we call this one over here? Point slope form. Now they're both lines. They both generate the exact same graph. There's no difference between the two. And if you don't believe that, that's okay, because you could take this line over here. This one's the easier one to mess with. If you take this line over here, check it out. I distribute the 2, and I get 2x plus 12 by distributing the 2 over here. Add the 4 to both sides. And you can see that they're the exact same line. There's no difference between the two of them. However, at one point when you learned about lines, you had to get used to the idea that sometimes lines are in point slope form and sometimes they're in slope intercept form. Just like at one point we all had to get used to the idea that 1/2 and 0.5 actually meant the exact same thing. So why do I bring that up now? Because let me actually move this down a little. This down a little. These are the exact same quadratic. Those are the exact same equation. They look different, just like the two lines look different, just like 1/2 looks different from 0.5, but they're exactly the same equation. They create exactly the same parabola. They have exactly the same ordered pairs. There is no difference between the two, except the way they look up there on the board. Now, if you don't believe that, and that's okay not to believe that because they look different, so I'm not sure I would believe it either, check out this one over here. Watch this. Does everyone agree that I can rewrite that x minus 3 squared as x minus 3 times x minus 3?
Yeah.
Okay, and I can FOIL that. And if I FOIL that, I'm going to end up with x squared minus 6x plus 9. Then I have to distribute the 2. Can't forget to do that. 2x squared minus 12x plus 18 plus 5. Collect like terms. 2x squared minus 12x plus 23. So I'm not trying to mess with anyone's head. What I'm trying to show is that we've seen this before, where two things are written in two different, where the same thing is written in two different ways. This equation and this equation are exactly the same. And if you're trying to figure out what I'm gearing towards here, this is kind of the way we're used to seeing me write it, like this. This is the way I introduced it to you. This is the way we've been talking about it. But this over here, this version, should not look completely foreign to us. In fact, what I'm hoping this version over here, this second one, reminds you of is it reminds you of the transformations we did back in the first unit, where you have a change on the inside, changes on the outside. So we have two major ways to write a quadratic. One of them looks like this. This is the one we were working with in class last time. The other one looks like this. And this one is similar to a transformation. So here's the problem, everyone. We need to be ready to work with whichever form they give us. But I'll tell you what, for the most part, people actually end up preferring this form right here. Now I prepared this next page ahead of time, just to save us a little time. And it's going to look very wordy, so don't try to copy all this down. The other reason I don't want you to try and copy all this down is because this is actually available on D2L as a handout, so if you can't read all this up here and you're saying, I'm never going to get through all that, there's a handout on D2L called Quadratics 2 Ways. And it's in the helpful handout section. So if you just want to look at a copy of this later that's maybe a little bit more clear, not so daunting up here on the board, go ahead and take a look at that. It'll be up there for the rest of the semester. And I'm not just going to sit here and read this to you, I just want to talk about some aspects of this with all of you. You see, here are our two different forms. We've got what we call standard form, and this other one over here is called the vertex form. Standard form and vertex form. And you know how A, B, and C can be numbers over here. We put in the numbers, we get our equation. That's the same thing over here with A, H, and K. The reason that we use A for both of them is because A is A. The number in front of your x squared over here is the same as the number in front of your parentheses over here. No matter which form you're written in, that A is going to be the same value. So what we have here, everyone, is we have an example of f of x equals 2x squared minus 16x plus 14. But I absolutely promise you that that's the same thing as f of x equals 2 times x minus 4 quantity squared minus 18. There is no difference between these two equations. Whichever one you're given, you need to learn how to work with. And that's very intimidating at first because we're just seeing this for the first time. And you're like, I can't believe all this stuff he has written up here. But I actually made this sheet to help you, not to frighten you. What's the domain of every quadratic, no matter what form it's written in? Negative infinity to infinity, that's right. And whether or not you're dealing with the form we did last time in this new form today, you've got that A value in front. And that A value in front still is responsible for telling you which direction it opens, up or down. That's not going to change. You still look at the number in front of the whole thing. That will tell you if you're going to open up or down. Last time we learned a formula for the vertex, negative b over 2a, and it took a little bit of work. Because after you used negative b over 2a, you had to run it through the function and get the y value. The really cool thing about this other form is the vertex is right in front of you. Check this out. This other form looks like this. And it actually gives you the vertex. There's no work to do to find it. The only thing you need to remember is that horizontal shifting was backwards. Does that sound familiar? We thought we should move a graph left when really we were moving it right and vice versa. So the vertex is right in here, and it's these two numbers. But the x value is the opposite of what you think it should be. So even though it says minus 4 and minus 18, the vertex is actually going to be 4, negative 18. Because the one on the outside for the y value, that's perfect. The one on the inside, you need to change its sign. We'll practice that today. Either way, once you have your vertex, you can write the axis of symmetry. How do you find a y-intercept, everyone? In general, how do you find a y-intercept of any function? You plug in 0 and you get the number that comes out. All right, now class, when you plug 0 into this other form, it's not just going to cancel everything except for the negative 18, and that's very, very treacherous. Everyone, if you plug a 0 in here, what's 0 minus 4?
0.
0 minus 4 is negative 4, agreed? What's negative 4 squared?
16.
16. 2 times 16? 32. Minus 18 is 14. Which means the drawback to this form that just spits out the vertex at you, the drawback to that form is it's harder to find the y-intercept. Because you can't just grab the number at the end. You actually have to plug in a 0 and crunch it out. Finally, what's usually the hardest thing to find no matter what form it's in? The X-intercepts. Yeah, they're tricky. If you can, you factor. If you're allowed to, you use the quadratic formula. If someone tells you you must, or you like it better, which I do, then you complete the square. Now it turns out when something's written in the vertex form, what you actually do is you use a technique which I like to call finishing completing the square, which I'm going to show you in our next example. I'm going to show you what I mean in the very next example. You'll notice at the very top of this page, and I know this is a lot of information, everyone. I don't expect you to be feverishly copying this down or reading this as I go. I do want you to be aware it's here so you can look at it later. And if you don't like that I marked this one up, there's a nice clean copy on D2L for you. But up here I actually try to make a little asterisk, the two different forms of a quadratic equation. There's actually another form of a quadratic that we often see in this class. And the other form that we sometimes see is a form where the quadratic is factored. Like that. So this right here this right here, and this right here are all different forms of the same equation. And they all have their upsides and their downsides. This one right here, it is very, very easy to give the vertex of 4, negative 18. This one right here, it is very easy to give the y-intercept of 0, 14. This one right here, it is very easy to give the x-intercepts of 7, 0, and 1, 0. They all have their advantages, depending on the form it's written in. What I want us to be able to do is work with one of these things no matter what form it's given to us. And we can. We can. But that's the idea, everyone. That was the main point of this page, was to just tell you this. If you walk away with something from this page, here's what I want you to walk away with. Quadratics can be written in different forms. And depending on the form they're written in, it might change the way we find information about that quadratic. So now if it's all right with you, I'd like to do just a concrete example of a quadratic and graph its parabola from start to finish. We'll talk about the things on here, and you, of course, can look at this later. It's in your notes forever now. This is one way of writing a quadratic. This is the way that I said we were going to learn today. Now, g of x equals negative x plus 3, quantity squared plus 4. What's the domain? I actually don't care what form it's written in. If it's a quadratic, what's the domain? Negative infinity to infinity, no problem. Which way does it open?
Down.
Down, because there's a negative in front of the whole thing. That's like our a value in front. So this one opens down. Here's the really slick part, everyone. The vertex is given to us. No one say it out loud. Everyone write down the vertex for this. Everyone write it down. Don't say it because I want everyone to have a chance to write it down. Write down your vertex. And it's right in front of you. You just need to remember to make one little change. What is the vertex, class? You can say
-3
it.
and 4.
Say again?
-3 and 4.
Negative 3 and 4. You change the sign on the x part, but not the y part. That's your vertex. Once you have your vertex, you can get your axis of symmetry. Your axis of symmetry is always a vertical line, x equals, and it's x equals the x value of the vertex. -3. Once you know which way your parabola opens, in this case down, and you know your vertex, is that enough to give the range of the parabola? It should be.
Yeah.
Yeah, this one goes down to negative infinity, and the highest y value it gets to is the y value of the vertex. In this case, 4. What's trickier on this one? The y-intercept. Because the y-intercept you have to find by plugging in a 0 for x. And I cannot stress this enough, how often people mess this up. Because people want the y-intercept just to be the number at the very end, but it's not. The y-intercept is found by plugging in a 0 for x, that's true. But when your equation is written in this form, everything doesn't just perish except for the last number. Because what you have here is you have 0 plus 3, which is 3. You have 3 squared, which is 9. It becomes a -9. You add 4 to that, and you get a -5. So our y-intercept is 0, -5. It takes a little bit more work to get it. Not a ton of work, not brain-destroying work, but it does take some work. So what don't we have yet that's usually the hardest thing to find? X-intercepts. Okay, now watch this, everyone. This is a trick. Would everyone agree that the way we usually find the zeros is we set the equation equal to 0 to start? And that's exactly what we're going to do, everyone. And here's what we're going to do. Move constant to other side and make sure you have a 1 in front of your parentheses. I know that's a lot of information here. You move the constant to the other side, so I'll subtract 4 from both sides. And then it says make sure you have a 1 in front of your parentheses. But what do we actually have in front of our parentheses? A -1. How do you get rid of a -1? You either multiply or divide by -1. It actually doesn't make a difference. I'll divide. So if I divide everything by -1, I'll get x plus 3 squared equals 4. What it said on the previous page, which I went through so fast so you might not have had a chance to read it, but what it said on that previous page is if you're trying to find the zeros of a quadratic written in this form right here, if you're trying to find the zeros of this, what you actually do is you finish completing the square. Because if you look at the point that I'm at right now, doesn't it look like I've been completing the square here from last time? In fact, what am I ready to do right now? I'm ready to apply the square root property. Let's do that. So I get x plus 3 equals plus or minus 2. I subtract 3 from both sides, and I get -3 plus 2 and -3 minus 2. You know what those are, everyone? Those are my zeros. Are they real?
Yes.
And if they're real, what else are they?
On the number line.
They're on the number line. Very good. They can be turned into X-intercepts. Now, I'm not going to tell you that you have to love this. I'm not going to say after this one example you're all experts. Here's a pop quiz. Don't worry, we don't take pop quizzes in here. But I will say that this kind of quadratic in this form definitely has a very set technique on how you can tear it apart also, not just the other one.
I just went through.
Oops. Let me go ahead and, I don't know, what this is doing here. Get out of here. Let me get a graph in here. Okay. What do we know? Do we know where our vertex is? Yeah, where's that vertex? Maybe you didn't write it down. Maybe you were just using my notes. Where's that vertex? Negative 3, 4. Okay. So negative 3, 4. Do we can put in our axis of symmetry now. Once we get that vertex in there. What else do we know? Do we have some X-intercepts? Yeah, those should be equal distance from the axis of symmetry. Looks good. Do we have a Y-intercept? Yeah, negative 5. We get a free point on the other side because these things are symmetric. So if we have that Y-intercept, we get a free point on the other side.
2.
If I wanted to plug in a negative 2 or a negative 4, I'm going to get 3. They'll both give me the exact same answer. This thing is symmetric. Is that enough information to sketch the parabola? Absolutely it is. Nice and smooth. No sharp points. Nice and smooth. Huh. That vertex, let me just label my vertex on here. That vertex is at negative 3, 4. Here's another question that someone might ask you about your parabola after you graph it. Increasing and decreasing. Where's the graph increasing? Where's it decreasing? Please remember, when you're doing these things, you're going left to right, and you're only looking at the x values, and you're only looking at parentheses. So you're going left to right, x value to x value. Or in this case, we are increasing from negative infinity all the way up to what x value? Negative 3. And once we get to negative 3, we start decreasing for the rest of the way. Old school, it's just that this time we generated the graph ourselves. It's kind of cool. If only there was a place where you could get more examples of these. Well, of course there is. Online. You go to D2L, you can find a YouTube link. 6 more of these. And not only are there 6 video examples of this, there are 3 video examples for the ones that look like this, and there are 3 video examples for the ones that look like this. That way you can watch them both. And there is a worksheet with an answer key. And why do I stress that? Because just doing the online homework does not help you practice your graphing very well. So you need to practice this by hand. All right. Before we walk away, I would like to do one more with you, if that's okay, to kind of show you something that might throw you a bit of a curveball. So this next one's not going to be as pleasant as the other 2. Here's our instructions for this problem. Do everything. All right, we're going to rip this thing apart. We're going to rip this thing apart. We're going to find out how it opens. We're going to give the domain. We're going to give the Y-intercept. We're going to give the vertex. We're going to give the axis of symmetry. We're going to give the range. And then we're going to try and find the zeros. And why do I say when we find the zeros that we'll maybe find the x-intercept? Why would I say that? Maybe, but what kind of zeros can we find that wouldn't be x-intercepts? Yeah, so if we find imaginary zeros, are they going to be x-intercepts? No, so we're going to find the zeros for sure. Can we always find zeros?
Yes.
Yes, but we don't know for sure they're going to be x-intercepts. So that's why I say maybe we'll find those. But some of this stuff, as you do more of these problems, is pretty fast. The direction it opens, is that pretty fast?
Yeah.
Yeah, this one opens up because of the positive 2 in front. The domain, it's like a throwaway question. Negative infinity to infinity. This form right here, it is very easy to spot the y-intercept. Because if you plug a 0 in here, everything dies except for what? The 4. This is a little trickier. Negative b over 2a equals negative 2. Oh, this is annoying. Negative 1/2. Well, I can't say I'm too happy about that. Is that possible? Could that happen to us? Could they hit us with a fraction? Yeah, they could. And if I put a negative 1/2 back into the function, then this is not the time. Well, maybe when you're doing your own homework at the time to try and do it for fun, but this in general is not the time to try and show off and try to do the math in your head. Because if you put a negative 1/2 in there, you got squareds in there, you got all these numbers running around, we got to figure out what this is. So this actually ends up being 1/2 minus 1 plus 4, or 7/2. If adding, multiplying, squaring fractions is something that you don't feel that great about, that's a great thing to have a quick talk with Rachel about during one of her sessions, or with me about during my office hours. If you're like, wait a minute, Steve, wait. One of us will be happy to help you with this kind of thing later, because it is tricky if you haven't practiced it in a while. Once we have our vertex, which is going to be negative 1/2, 7/2, what do we get the axis of symmetry for free?
Yeah.
Yeah, it's just going to be x equals negative 1/2. We also get the range for free. This thing goes up to infinity. And the lowest y value it ever gets to is 7/2. Now I want you to think about this for a second, everyone. Before I find the zeros, I want to show you something. I want to show you something in here that's very interesting. Edit. Wait a minute. Am I on the right page? Lost my page. Okay, cool. Edit, paste. Now, this has a vertex of negative 1/2, 7/2. You don't need to like that, but that is where it is. Right here. And which direction does this parabola open? Up. If this parabola opens up, and it has its vertex right here, how many times are we going to hit the x-axis?
No, 0.
Yeah, it doesn't look like we're going to hit the x-axis at all. And if we don't hit the x-axis at all, we don't have any x-intercepts. What does that tell you about our zeros? They're going to be imaginary. We should still find them, but they're going to be imaginary. Well, all right. 2x squared plus 2x plus 4 equals 0. I guess I could use the quadratic formula, but I would actually say on this problem, this is a very good opportunity to complete the square. And I'll tell you why. Look at this. subtract the 4 from both sides. And if I'm completing the square, what's the next thing I do?
Take it 2.
Divide by 2. And is this one easy to divide by 2?
Yeah.
Yeah, it's really slick to divide this one by 2. Take the 1 off to the side that's in front of the x. Cut it in half. Well, this part I'm not too happy about. Square it. Get 1/4. Add 1/4 to both sides. I'm going to do this kind of fast, everyone, because I want you to have this in your notes, but this is not the main focus of this problem. 1/2 squared, 7/4. Apply the square root property. That should be negative 7/4, sorry. Yeah, they do end up being imaginary. Now, if someone asked me to graph this thing, then I really don't need to do that, unless they specifically said, tell me the zeros. But what I'm trying to graph, what I'm more curious about is X-intercepts. And because you're all so smart, you realize we didn't have any X-intercepts, because if the vertex is up here above the x-axis and this thing opens up, we're not going to have any X-intercepts. So just as we thought, there are no X-intercepts because those are imaginary zeros. Do we know anything else? This is terrible. Do we know anything about this equation? Do we have any other points? Do we have a y-intercept? Yeah, that's at 4. But good luck trying to draw this parabola. So what do? If someone's telling you you have to draw this parabola and this is all you have, what do?
You can plug in more points.
Yeah, you can plug in more points. And I'll tell you, even though the zeros are imaginary, this is not that ugly of an equation. Does everyone see that? That's not that ugly. It's not that bad to plug numbers in there. You could plug like a 1 in here, for instance, and if you plug a 1 in here, you're going to get an 8. If you plug a negative 2 in here, you're going to give an 8. And as soon as you get those 2 points right there, things start to look up. Suddenly, we have a graph we can draw. Why? Because we didn't really have enough information with just the vertex, and that y-intercept so close to it. But just by finding that other point and the one on the other side, we get a pretty slick drawing. So even if you don't get all the information that you need from kind of all this stuff up here, if that doesn't tell you everything you need to know, remember, you can always find more ordered pairs. And you don't just plug in any x value, even though you're allowed to plug in any x value. You wouldn't want to plug a 5 into this thing, because that's going to give you some ordered pair that's way up here that you can't even graph well. I plugged in numbers like 1 and negative 2. Why? Because they were close to the vertex. Once you have that vertex, that's the most important point. I would argue if you had the vertex, you could just start plugging in more x values, moving away from the vertex, and you could get a pretty good parabola. So never be afraid to find more ordered pairs for yourself. And you'll do okay. Questions, comments? Well, I have a couple comments for you. Oops, that's not what I wanted to do. This part of the lecture is called the worst homework problem in section 3.1. And I'll tell you why it's the worst homework problem. Because if it truly was the worst homework problem ever, I just wouldn't have you do this problem. I would say, we're not going to do this homework problem. The thing is, it's actually a really, really cool homework problem that has one terrible part in it. Don't worry, it's nothing like offensive, it's just mathematically annoying. It's actually this really, really neat idea where it's an application problem. So this kind of answers the question for everyone that asks, when are we ever going to have to use this math? This one actually answers that question, because What it's about is it's about using parabolas and quadratics to figure out the best way to make a parking lot, so you use the least amount of materials and get the biggest parking lot. It's actually a pretty awesome problem. And I don't want to tell you all about it because I want you to fight your way through it a little bit, because for the most part I think it's a really good problem. But here's what I want to warn you about. When you get down to part D of the problem, you will see the nastiest looking multiple choice question you've seen in a while, right here. And it's just got all these decimals in it, and it's very tempting to say, what are they even talking about here? What's going on? What this is basically about, everyone, is this is about doing guess and check with a calculator. So don't let this part of the problem freak you out. It's actually a pretty cool problem about building a parking lot. You get stuck on it, you send me an email, ask my teacher, or you ask for the help me solve this or show me an example, you get some help. That's okay. But as I said, this part right here might give you a headache. But don't let it bother you too much. Just use a calculator to do some guess and check. I just want to give you a warning so your weekend didn't get ruined while you're trying to do this problem. This one's even cooler though. This problem I really like. Here's another problem I want to show you. This is a really cool applications of quadratics. If an object is projected upward from ground level with an initial velocity of 48 feet per second, so we're launching an object up from the ground. If you're like me, whenever you heard a problem like this in college algebra class, you got the cold sweat and you start to zone out a bit, but stay with me just for a minute. We're going to launch an object upwards, and it says that this function right here tells us how high the object is at any given time in seconds. So t is in seconds. The function itself gives us feet. So everyone, I just want to show you how this function works. They give us this function. We're launching an object up in the air. And of course, on Earth, if you launch an object up in the air, what's going to happen to it? It's going to go up, it's going to hit a highest point, and come back down. So, if you plug numbers in here, we'll tell you what's going on. Look at this, everyone. If you plug a 0 into this function, what do you get? This is not a trick question. What do you get? 0. And the reason for that is because at 0 seconds, it is 0 feet in the air. How do I know that? Because it said it was launched from ground level. So when no time has passed, it's still sitting there on the ground. What's going on with it? Well, if you want to know what's going on with it, plug a 1 in here. If you plug a 1 in here, you're going to get 32. How do we interpret that? At 1 second, this object is 32 feet in the air. So, what they are asking me, everyone, is they're asking me to find the number of seconds it will take for it to reach its maximum height. And then they want to know what is that maximum height. Everyone think about this equation right here. This is a quadratic. Which way does it open? Down. If I draw a parabola that opens down, and I start throwing around the word maximum, what does that make you think of on this parabola?
It's a vertex.
The vertex. The other thing about story problems is this. Story problems you encounter in a math class almost always are asking you to do something you know how to do already. You just need to figure out what it's asking you to do. This thing might as well say this. It might as well say S of t equals negative 16t squared plus 48t. Give the vertex. That's what it's asking for. And do we know how to find a vertex? Yeah, we sure do. What's that formula for finding the vertex? Negative b over 2a. Well done. So that's going to be negative 48 over 2 times negative 16. That ends up being 1.5. Oh, I get it. This thing's going to go 1.5 feet up in the air. Wait, do I get it or am I confused? What does that 1.5 represent? the seconds. That's how long it takes to get to its maximum height. So that's the x value of the vertex, but that means 1.5 seconds to maximum height. Well, how do you find the maximum height?
Plug that back in.
Plug that back into the function? You got it. I'd be pleased and proud to do that for all of you. And if you plug that back in, yes, you got to do a little bit of work. You got to do some squaring, you got to do some multiplying, but when the dust all settles, you will get 36. Oh, so I get it. After 36 seconds, this thing is 1.5 feet in the sky. What do you mean by that? Oh, sorry. This is the feet. The vertex is 1.5, 36 seconds, max height in feet. Do not let story problems ruin your day. As I said, they are almost always asking you something you already know how to do, like find a vertex. We just need to make sure we can read it and translate that's what they're looking for. So rather than thinking about how much a story problem annoys you, which it might, think about what parts of this do I recognize? I recognize that quadratic right there. I recognize it as a graph that's a parabola. I recognize that it's a graph of a parabola that opens down, which means the vertex is the highest point. And they're asking me about a maximum. I think they're asking me about the vertex. And that's exactly what they want to know. This is informally. I mean, you might still have some questions to ask Rachel or myself during office hours or during Rachel's sessions, but this is informally the end of section 3.1. So when we come back, we'll start our next section at 11:31. Moving on deeper into chapter 3, it's been my experience that the sections 3.2 and 3.3 sort of blend together. I feel like when I'm teaching 3.2 without talking about 3.3, I'm like holding back information that actually makes 3.2 much more clear. So I do kind of teach these sections together. So it's going to be sort of unclear which section I'm in, but after we're done with this, you'll be able to make your way through both sections pretty well. This is mainly about our polynomials now. We're moving away from the quadratics, which are degree 2 polynomials, and we're going to be moving on to polynomials that are mainly degree 3 or higher. So remember, the degree of a polynomial just means the highest power you see, and that's what we're going to be talking about. But first, a little recap here. You can have a degree 0 polynomial. And a degree 0 polynomial is just a horizontal line. And the reason that works, everyone, is because a horizontal line is just going to be f of x equals a number, maybe a positive number, maybe a negative number. But it turns out, everyone, that you could rewrite this, and no one ever does this, but you could rewrite this as negative 3 times x to the 0, or 2 times x to the 0, because anything to the 0 power is 1. So therefore, putting an x to the 0 is like multiplying it by 1. The reason I'm doing this is not because you're going to see this very often, but just to show you that yes, 0 is the highest power, so horizontal lines are considered degree 0 polynomials. The good news is we don't usually need much help graphing those once we've learned how to graph them. They're horizontal lines. A degree 1 polynomial is a line that is not horizontal or vertical. In other words, if you just want to say it's a slanted line, that's probably the easiest way to say it. It's a line that's slanted. It's not horizontal or vertical. That's considered a degree 1 polynomial. And the reason for that is because the equation for a line looks something like this. And even though we don't write it on there, we do know that when someone doesn't write the power, that really is a power of 1 up there. But once you learn how to graph a line by plotting a couple points or using the slope and using the intercept, You don't need a lot of fancy tricks to help you graph a line. I'm not saying it's the easiest thing in the world, but I am saying once you learn how to do it and you have a technique, that technique will work for you. And it's not that bad to graph a line once you get the hang of it. We know what a degree 2 polynomial is. A degree 2 polynomial is a quadratic. And as we kind of know now, we're going to see our quadratics in kind of 3 different forms. Sometimes we'll see them written like this. That's kind of the standard way to write them. Sometimes we'll see them written like this. That's the way where it's kind of easy to spot the vertex right off the bat. And sometimes we'll see them written like this. Kind of 3 different ways we might write a quadratic, but all of them are degree 2 polynomials, because all of them could be written like this, top one h of x, if you just multiply it all out. And as you move on, the other ones do actually have names, but I don't really use the names very much except for the 3rd degree. But if you have a degree 3 polynomial, that's actually called a cubic. A degree 4 polynomial, just for your own personal amusement, is called a quartic. And a degree 5 polynomial is called a quintic. But I'll tell you, I don't really use the word quartic or quintic. You won't really hear me use those words at all in this class. I do use the term cubic for a 3rd degree polynomial. But if you ever get confused, you really can just call them by the number of the degree. You can say this is a 3rd degree polynomial, this is a 4th degree polynomial, this is a 5th degree polynomial. Why do we like polynomials so much? Well, one thing we already know about them is all polynomials have domain what, everyone? What's the domain of every single polynomial ever? Negative infinity, infinity. Any single polynomial you ever write, you can plug any number you want into, it's fine. All polynomials, degree 2 or higher, are smooth curves. Nice rounded smooth curves. No sharp corners, no straight parts, just all curvy. This one I talked about last time, and I'll put it up here again. Only the quadratic has a graph called parabola. Only the quadratic gets the parabola. Otherwise, it might be something that looks sort of like a parabola, but it's not. Only if it comes from a quadratic. We did a little bit of that last time. And here's the last thing I'll say about these. All polynomials of odd degree, if the highest power is odd, have range negative infinity to infinity. If it's an odd degree, everyone, then it does go up and down forever. The quadratic wasn't odd, so it didn't do that. All even degree polynomials will have a highest or lowest point. So the range will be either something like a lowest number up to infinity or negative infinity up to a highest number. Just like the quadratic topped out or bottomed out, the parabola did. That's actually going to happen with every even degree polynomial. If the highest power you see is an even number. All right, so that's kind of some basics about polynomials. Let's get a little bit deeper into what we can tell about polynomials. And this might be some things that some of you are already thinking, or give you some new things to think about. A polynomial can have up to as many X-intercepts as its degree, but no more. It could have less. A polynomial can have as many x-intercepts as its degree, but it could have less. Oh, wait. Quadratics. Quadratics had 2, 1, or 0 x-intercepts. That's the best example of this right here. Any polynomial you ever draw can have as too many x-intercepts as its degree, but it will never have more. So a quadratic is a degree 2 polynomial, so it could have 2 x-intercepts. But did that mean it had to have 2 x-intercepts? No, it could have had just 1, or it could have had none. So anytime you draw a polynomial and you're wondering about its x-intercepts, you can never say it has more x-intercepts than its degree. Never. So here's a polynomial. And I'm going to ask you a couple questions about it. And the answer to the first question is one of the easiest answers you can ever give. Because my question is this. How many x-intercepts does that polynomial have?
2.
And what's the easiest answer to give in a math class? I don't know. Because you don't. We don't know how many it has, but you can answer this question. What is the maximum possible number of x-intercepts this one could have? 4. But if I say how many does it have? I don't know. I really don't know. I just made up this equation. I don't know. But I can say this. Degree 4 has at most 4 x-intercepts. Could have 4, 3, 2, 1, or 0. I don't know how many it has. I will tell you this though, and this is true, everyone. Since odd degree polynomials have range negative infinity to infinity, they always have at least 1 x-intercept. That is true. Any function that has a domain of negative infinity to infinity and a range of negative infinity to infinity is going to have to hit the x-axis. As long as it's a nice polynomial, smooth and continuous. All right, so this isn't that profound. This is just me saying you can look at the degree and you can know something. You can know that this might have 4 x-intercepts, but that doesn't mean it does have 4 x-intercepts. Just like you can look at a quadratic and say it might have 2, but it might not have any. All right. Now, let's say someone gives you this. This is the same one I had on the previous page, I believe, yes? And they want to know 2 pieces of information. They want to know the y-intercept, and they want to know the x-intercepts if it has them. Class, which one would you rather find, the y-intercept or the x-intercepts? The y-intercept, me too. I'll tell you why I'd rather find the y-intercept. Check this out. H of 0 equals negative 12. 0, negative 12. Done. This is not a quadratic. You can't use the quadratic formula. This is not a quadratic. We cannot complete the square. If we can't use the quadratic formula and we can't complete the square, what was our only other option for finding the zeros? Well, you could guess and check, yeah, but what was the other way for a quadratic that we found zeros other than the quadratic formula, other than completing the square? Starts with F. Factoring. So, factor h of x. All right, I want to factor that real quick. But stop mumbling, factor it. Oh. Is it difficult to factor a 4th degree polynomial? Yeah, it is. That's not an easy task. Which is why we're going to spend quite a big chunk of our lecture learning how to factor them. Me telling you just to factor this is a jerk move. But I'm going to teach you how to factor it. Now, using technology before class, I factored this thing. And when I factored it, I got this. But there is nothing trivial. There is nothing simple. There is nothing that just allows me to do it with a wave of my hand that says you can easily go from here to here. That is not a trivial thing. That is not an easy thing. That is not something I can just ask everyone to do on a whim. But they are identical equations. This is just a factored form. But in general, it's not easy to go from this original form to a factored form. But once it is factored, is it pretty easy to identify the zeros? Yeah. Once it's factored, I can see that the zeros are -2, -1, and 3. Because what I'm doing, everyone, is I am mentally figuring out the numbers that will make each one of these factors equal to 0. It's not the number you see in the factor. This says x plus 2. Yes, I know that. But when you're asking for the 0, you're asking for the number that will make the factor equal 0. So that's why I write down -2. Now, does everyone see how this factor right here shows up twice? But I only wrote down -2 once? We actually have a word for that. I'm going to teach you more about this word later, but for right now, I just want you to keep it in the back of your head. What you would say is you would say, this 0 has multiplicity 2. And all that means is the factor showed up twice. That's what that means. The factor showed up twice. Factors give us zeros. And if the zeros are real numbers, what else are they? Are they X-intercepts? Yes, they are. So our X-intercepts are -2, 0, -1, 0, and 3, 0. All right, so what I want you to be walking away from this part of the lecture with is, this is not easy. That's why we're going to spend some time learning it in class. Going from h of x equals x to the 4th plus 2x cubed minus 7x squared minus 20x minus 12 to h of x equals x plus 2 times x plus 2 times x plus 1 times x minus 3. That's not an easy thing. Let's get some vocab clear before we move into this, because I want to make sure everyone's on the same page. What is a polynomial factor? What is the factor of a polynomial? It's going to look like this. X plus a number, or x minus a number, or just an x. A factor of a polynomial is going to be x plus a number, x minus a number, and every now and then it will just be an x, but it does have to have an x in it. If it helps you, you can think of this one right here as x minus 0. So it does look the same, it just, we don't bother to write the 0. That's what a factor is. What is a 0? Well, there's a couple ways I can answer that, but the way I want to answer right now is it is the number that makes the factor 0, and then the whole function. A 0 is the number that makes the function equal 0, but on a smaller level, the 0 is the number that makes the individual factor equal 0. Because if you make the factor equal 0, then it multiplies by all the other factors and kills them all off. So a 0 is still a number that makes a function equal to 0, absolutely. But if you want to look at like the kind of what's going on under the hood, you say it's making an individual factor equal to 0. What is an X-intercept? It is the ordered pair, where you write the 0, comma 0, if the 0 is real. So here's what I want you to take away from this, everyone. Factors, zeros, and x-intercepts are not exactly the same thing, but they are very closely related to each other. It's not the same thing to say this is a 0, this is a factor, this is an x-intercept. You really can't do that. But you could say they all go together. That's okay. To the point where I'm actually going to show you a little table. Look at this. Look at this right here. All right. Let's say we know x minus 7 is a factor of our polynomial. What's the 0 that goes with that factor? 7. What's the x-intercept that goes with that 0? 7 comma 0 is an ordered pair. Everyone with me so far? Let's say that negative 2 is a 0. What's the factor that goes with negative 2? Careful. X plus 2. Good. X, not 7 plus 2. X plus 2, yes. What's the x-intercept? 2. Negative 2, 0. You see, if you know one, you know the other ones. Here's a trickier one. What if the factor is just x? What do you think the 0 is then?
1. Negative 1.
What's the number that makes x equal to 0? 0. The 0 is the number 0 then. And the x-intercept is 0, 0. By the way, that's also the y-intercept. The origin, the point right in the middle of everything on the coordinate system, is an x-intercept and a y-intercept. It's both at the same time. How about this one? 2i. This is not a trick question. The way you get a factor is you just do x minus the 0. We can write this as a factor. So the factor to this is going to be x minus 2i. That's perfectly allowed. This is a trick question. What's the x-intercept? None. That one is not an x-intercept. It is still a factor. It is still a 0. It's just not an x-intercept. How about this one? Negative square root of 7. What would the factor be? Careful. The factor. How do you get a factor? Everyone, watch this. The way you get a factor every time, the way you go from here to here, is just x minus the 0. In this case, you are subtracting a negative. So what's it really going to be? X plus the square root of 7. It's okay if you're struggling with this a bit. That's why we come to class, so we can learn this stuff and then we can do better later. Does this one have an x-intercept? Yeah, because it's a real number. It's not one I really feel like graphing today. Let me make sure you can really see that negative sign in there. All right, so this is the relationship between factors, zeros, and x-intercepts. You don't need to love it, but that is how it works. Here's a little tip for everyone. The 0 will have the same sign means positive or negative, will have the same sign as a 0 or an x-intercept. So it should look exactly the same as a 0 or an x-intercept. That shouldn't change the sign. Where the sign changes is when you go between 0 and factor. That's where it has a different sign. That's where you go back and forth between plus and minus. Little hot tip for all of you there. And it's nothing sinister. It's just because the 0 is the number that makes the factor equal 0, so that's why it needs to have the opposite sign. All right, let's travel back in time. Some of you might not want to go this far back in time, but it's important to me that we're all doing this together. How do you factor the number 20? What do you do first?
Negative 20.
You can boil it into two factors. What are two numbers that multiply to give you 20? Just give me two. 10 and 2. 10 and 2, okay. Are you done factoring yet?
No.
Not really, because you can break the 10 up even more. So really, you can break this up into 2 times 2 times 5. And how do you know you're done factoring a number?
You can't factor 5 anymore.
Because they're prime numbers. Done because prime. Well, you're done factoring a polynomial when all of your factors look like one of those three things: x plus a number, x minus a number, or just x. That's how you know you're done factoring a polynomial. What is a factor? It's something you can divide into the whole and get remainder 0. That's what a factor is, everyone. A factor is something you can divide into the whole and get a remainder of 0. Two is a factor of 40 because 2 goes into 40 20 times, remainder 0. 3 is not a factor of 40 because 3 goes into 40 13 times, remainder 1. Here's what I meant when I said we're going back in time. We're just reminding ourselves some vocab here. What's the meaning of a factor? A factor is something you can divide into the whole and get a remainder of 0. If you don't get a remainder of 0, it's not a factor. If you do get a remainder of 0, it is a factor. The factors of a polynomial that we want are called linear factors because x minus c, x plus c, and x are all first degree. In other words, if you said y equals to any one of those, they'd all be lines. So our polynomials are going to have factors called linear factors. All right. Now, class, if I gave you this, and asked you to factor that number that's over 5 million. And I said, and this is not true anyone, but I said, that's the only thing you have to do to get an A in this class. Could you all sit down and do that if you needed to?
Probably.
Probably. But do you know off the top of your head what the factors are?
No.
No, but how would you start?
Probably 2.
You divide by 2. Why would you divide by 2?
It ends in an even number.
Because it's an even number, so you know 2 is a factor. So if you had to factor this, you'd start by dividing by 2, a known factor, and reducing to a more manageable number. In fact, if we divided this by 2, who's packing heat? Who's got a calculator? Anyone? Someone divide this by 2 for me.
What's the number again?
5863484.
2,931,742.
Thank you. Now we're not going to take this all the way down. Don't worry. I want to bore you out. But what would you do next? You divide by 2 again because it's still even. And would you continue to get it smaller and smaller? Yes, you would. Then I divide by 2 again. So that's the point, everyone. Every time you pull a factor out or start to divide by factors, you're making whatever's left more manageable, easier to deal with because you're breaking it down. It's going to be the same thing with polynomials. Now, this part's a little sticky. But we do have to do this. I know, because I picked this one, that this polynomial, this quadratic, factors to x minus 5, x plus 3. Not only are those the factors, but those are the unique factors. There's no other way to factor this thing. Just like there's only one way to factor a number, there's only one way to factor a polynomial. Now, that means, I'll just pick one of them. Since x minus 5 is a factor, and I just picked one of them at random, that means that x minus 5 divided into x squared minus 2x minus 15 should give what remainder? If it is a factor, what should my remainder be? 0. It should be. Now, before anyone flips out, you might have flipped out a little bit while you're doing the pre-work for this. We do not do a lot of long division in this class, but I am going to do it here once. You divide x into x squared. X squared divided by x is not 2, it's x. A lot of people think it's 2. I'm not making fun of you if you were thinking that, but that's not what it is. Then you multiply this back through. This is just standard long division, not our favorite thing, but it's still doable. You multiply it through back both terms and you write it there. Then you rack this up and subtract it off. That means x squared minus x squared is 0. Negative 2x plus 5x is 3x. Bring down to negative 15. Then you divide x into 3x. That's 3. So you write a plus 3 up here. You multiply that back through, and you get 3x minus 15. You subtract that off, and you get 0. Wait, is that what I wanted to have happen? Yeah, not only did I get remainder 0, but I got the other factor. So, divide by a factor, get remainder 0, and break down the original function. Not only did I just show that x minus 5 was a factor, but I also got the other factor. All right. So, look at this. Look at this. Little vocab, everyone. This equation right here, x squared plus 2x plus 1, factors is x plus 1, x plus 1. Now I'm going to divide this equation, x squared plus 2x plus 1, by x plus 4. Is x plus 4 a factor? Not a factor, only x plus 1 is a factor. Does everyone see that? Basically what I'm about to do, everyone, is I'm going to try and divide the number 9 by 4. I can do it, but it's not going to give me a remainder of 0. Does everyone see that? Little vocab for everyone. This is going to be called the dividend, the thing you're dividing into. This is called the divisor. I don't know what my remainder is going to be, but I can tell you one thing. My remainder is not going to be 0. Just like I know if I divided the number 3 into 10, I know 3 is not a factor of 10. So I know my remainder is not going to be 0. X goes into x squared. You can still do this though. Gives me x, multiply that back through. X squared plus 4x. Wrap it, subtract it. X squared minus x squared is 0. 2x minus 4x is negative 2x. X goes into negative 2x, negative 2 times. Multiply that back through. You get negative 2x minus 8. Wrap it, subtract it. You get 9. What's the punchline here? Quite simply, here's the punchline. X plus 4 is not a factor. Our quotient, our answer, x minus 2 is not a factor because I didn't divide by a factor, so I didn't get another factor. Remainder was 9, not 0. If you can divide something by saying it's not a factor, but that doesn't give you another factor. That's okay. If I divide 10 by 3, I'm going to get 3 remainder 1. Well, neither your quotient, the answer you got, nor what you divided by was a factor. It doesn't mean you did bad math, it just means you didn't learn any factors. So here's the idea, everyone. In general, we test for factors by dividing and hoping the remainder is 0. If you divide something by something you think might be a factor, you hope that the remainder is 0. That means it's a factor. Great. But no one, myself included, wants to do this all day. That's terrible. It's mathematically kind of cool, but it's a terrible way to spend your time. So, we can check if x plus a number or x minus a number is a factor of a larger polynomial using synthetic division. Synthetic division class is a fast, efficient, fairly free of mistakes way, I mean, you can always make an arithmetic error, but this one's much easier not to make a mistake, of determining whether or not something is a factor of a polynomial or not. I'm going to show you how it works right now. Now, the question I'm going to ask is x minus 5 a factor of x squared minus 2x minus 15? And yes, it is, because I did this exact same problem before with long division. And I got x plus 3 as my answer with a remainder of 0. So yes, it was. Why do I do the exact same problem again? Because I'm going to show you a different way to do it, and it's helpful to see one when we already know what the answer should be. So, class, here's what you do. You make a little box up here, and in here, you write the 0 of your divisor factor. So that thing that you're testing to see if it's a factor, the number you write up here is the 0 of that factor. So this is x minus 5. So what would be the 0 associated with that factor?
5.
5. So we write a 5 up here. Then next to it, in a row, right here, you do the list of coefficients of the polynomial that you're dividing into in descending order. Now this polynomial is already written in descending order. That just means the powers get smaller as you go left to right. So what we do is we list the coefficients. Check it out. 1, minus 2, minus 15. Where did those come from? 1, minus 2, minus 15. Then, leaving space to write another row of numbers, you put a line in here, but there should be a space to write another row of numbers between these numbers and that line. Long division's a pain in the neck because there's so many steps. You divide, you multiply, you subtract, you bring down. You divide, you multiply, you subtract, you bring down. There's negatives running around everywhere. It's so easy to make a mistake. This is much better. This is just these two steps. Add, multiply, repeat. Add, multiply, add, multiply, done. So, first thing you do is you add this to nothing, and you just bring it down here. So basically what you do is you do 1 plus nothing, everyone. 1 plus nothing, the 1 comes down. Some people say bring down. I like to say add because that way I can just say these are the two steps, back and forth. Then, to get your next value, multiply bottom number by the number in the box. So to get your next number, everyone, you multiply this bottom number right here times the number in the box. 1 times 5. What's that going to be? 5. That goes here. That was multiply. What are we supposed to do next after we multiply? Add. Negative 2 plus 5. What's that going to be? Positive 3. I just added. What's the next step? Now when you multiply, though, you always go back to the box to multiply, but you use your most recent number down here. So, to get your next value, multiply the bottom number, and that's the one farthest. I'll just say your newest one. Your newest number on the bottom row. So our newest number on the bottom row is 3. We multiply that by the 5 up here. What's 3 times 5? 15. What's negative 15 plus 15? Does anyone know what that 0 represents? What did I want to get a remainder of when I did this problem? 0. That right there, everyone, is your remainder. The quotient is in the bottom row. These numbers are the coefficients on a polynomial 1 degree smaller than the dividend. And the other word for the dividend is the big guy you divide it into. So everyone, we divided into a degree 2 polynomial. Here's the easiest question I'll ask you all day. What's 2 minus 1? How dare you be quiet when I ask that? Yes, it's 1. That means our quotient is a degree 1 polynomial. Our quotient is a degree 1 polynomial with these as its coefficients. In other words, that 1 and that 3 you see in the bottom row become 1x plus 3, or just x plus 3. That's our quotient. Is that what we expected to get as a quotient? Yeah, because that's exactly what we got with the long division. All right. How about this? How about this, class? Is x plus 4 a factor of x squared plus x, I'm sorry, plus 2x plus 1? No. We already did this with long division. But the long division took a while. I'm going to show that it's not a factor using synthetic division. Watch this. What number goes up here in the little house? Is it 4 or negative 4? Negative 4. It's got to be the number that makes this guy equal 0. The numbers I list over here are 1, 2, and 1. Add. What's 1 plus nothing, everyone? 1 plus nothing. 1. After you add, you multiply. So always multiply this by newest value on bottom row. So negative 4 times 1? Negative 4. Add. 2 plus negative 4? Negative 2. Multiply. Negative 4 times negative 2? Positive 8. 1 plus 8? Same remainder as before. 9. Same quotient. 1 minus 2 converts to x minus 2. Not a factor. That's the exact same information we got when we did this problem before using standard long division. I did it at some point. Here it is. That's the exact same answer I got before. X minus 2 with a remainder of 9. X minus 2 with a remainder of 9. So class, if I may here in the last 4 minutes, let me show you something. H of x equals x to the 4th plus 2x to the 3rd minus 7x squared minus 20x minus 12. Factor, knowing that x plus 2 and x minus 3 are factors. When I gave you that big number before that was in the millions, and I asked you how would you start factoring this, someone said, I think it was over here, you said start with a 2 because it's an even number. You had a clue, you knew an idea of where to start. Does everyone agree with that? Now the clues don't come quite as easily with equations, so sometimes someone has to give it to you. So I'm giving you a clue. I'm saying, I want you to factor this. But rather than you just having to guess and check factors, I am telling you 2 of the factors you can start with. So what you would do is you would take one of these. It's actually a little bit easier to see what happens if you do 3, but you can do them in either order. And you divide. Synthetic division, everyone. And you might think this looks daunting, but let me remind you of something. It's just 2 steps back and forth. Add, multiply, add, multiply, add, multiply. And maybe you mess up the first few times you do it. But since I'm promising you this right here is going to work, what should our remainder be? 0. It should be 0. Bring down the 1, or add 1 to nothing. 3 times 1, everyone. 3 times 1. 3. Add. 5. Multiply. 15. Add. 8. Multiply. 24. It's okay, it's late in the day. Negative 20 plus 24? 3 times 4? 12. And we are on our way because not only do we know that x minus 3 is a factor, But just like with numbers, we have started to break down the big guy. Because this right here represented a 4th degree polynomial. And whether or not you remember me saying it or not, I said that when you do this division, your quotient is going to be 1 degree less. So what does this represent right here? What kind of polynomial? A 3rd degree polynomial. This right here is your remainder, but the 3rd degree polynomial that you have is x cubed plus 5x squared plus 8x plus 4. Not only do we have a factor pulled out, but we have started to break it down. And I would love to have a few more minutes to finish breaking this down with you, but we are out of time. So we're going to pick this up next time. Sound okay to everyone? Have a great weekend, and thank you so much for coming.